So my name is Christophe FINOT, and my talk will deal with the concept of nonlinear pulse shaping carried out in an optical fiber. So I will present results that have been obtained with my close collaborators Kamal Amani, Julien Ferthaume, Bertrand Kibler and Gouy, all from the Laboratoire Interdisciplinaire Carnot de Bourgogne of the University of Burgundy in Dijon in France. We have also benefited for various long-term and very fruitful collaboration with Professor John Dudley from the University of Franche-Comté, with also Stefan Wamnitz from the University of Brescia, also with Sonia Boscolo and Hervé Rignot. My talk will be organized as follows. As an introduction, I will recall different concepts that are needed in order to well understand this concept of nonlinear pulse shaping. So I will first recall what a spectrogram is, and then I will present what can be achieved using standard linear shaping. And then I will recall how pulse can evolve during its nonlinear propagation in an optical fiber. After this introduction, I will present two examples of waveform generation using nonlinear shaping. The first example will deal with parabolic pulses, and the second example will deal with the generation of triangular pulses. And in the last part of this talk, I will present some more recent results where we have generated a pulse that we have called a flaticon. So a spectrogram is a time representation of an optical signal. This quantity is quite easy to calculate. You take the signal that you want to analyze, you slice it using a temporal gate, and then you consider the Fourier transform of this temporal gated signal. It can be experimentally generated using an X-frog device, and what is nice with the spectrogram, this is that you can directly visualize how the energy is spread in the frequency and time domain. It is also easy to visualize the temporal and spectral shift, as well as a transform limited pulse. In this case, for a transform limited pulse, what you will observe, this is a vertical or an horizontal line. Linear shaping is usually carried out in the spectral domain. And starting from, let's say, a Fourier transform spectrogram, you can attenuate some various spectral components. So in this case, you can shape directly the spectrum of your pulse. But you can also play with the phase, and you can apply some delay, in which case you will move the energy along the temporal axis of the spectrogram. So this linear shaping is extremely powerful approach and is already used in several branches of physics. But even if this sounds quite simple, generating a waveform such as a triangular or a parabolic pulse is in fact rather difficult with linear shaping due to the ripples that are present in the spectrum. Indeed, there are some restrictions in the linear shaping. So the first, this is that in order to perform your shaping in the spectral domain, you need a pulse with a large spectrum. So typically, you will have to use pulses that are a few hundred of femtosecond. Then the process is based on inducing dissipation, so you will lose a lot of energy during the shaping of the spectrum. And one last restriction, this is that you can just move your energy in the spectrogram along the temporal axis. There is no way with a linear shaping to move energy outside the initial spectrum. So one direct consequence is that this is absolutely not possible to generate pulses that are shorter to the input pulses. So the idea of the nonlinear shaping, this is to use a nonlinear effect. In our case, we will use the Kerr effects in order to gain some flexibility along the frequency axis. And typically, we will use an optical fiber in order to tailor the content of the pulse along the frequency and time axis. So the optical fiber, they are a very good device to use the Kerr effect because they are costless and they are now widely available. So we'll just here we call briefly how we can model the propagation in an optical fiber. So the most basic model that you will take will include the effect of the dispersion as well as the effect of the nonlinear coefficient, the effect of the Kerr nonlinearity, and it will give you the well-known nonlinear Schrödinger equation. You can have another degree of freedom by also including some optical gain along your fiber, for example, if you use a Raman distributed gain. So in this case, you will add an extra term of gain in your nonlinear Schrödinger equation. So what you will have, this is an equation that seems very simple, but with such a simple equation you already have a lot of possibilities. There is an extremely rich dynamics that can be observed. And to reduce the number of parameters, you can use some normalization of this equation, and it will help to provide some efficient guidelines for the design then of the nonlinear shaper. So I will not go into the details of this normalization and how we can find those guidelines. Briefly, how will the dispersion impact the propagation of an optical pulse? So here I will consider the effect of dispersion alone, and what we can see this is that dispersion induces a delay between the different spectral components, so it stretches the pulse along the temporal axis. The slope will depend on the sign of the regime of dispersion. According to the regime of dispersion, depending if you are in the normal regime of dispersion or in the anomalous dispersion regime, you will have opposite slopes. In this presentation, I will focus on the nonlinear dynamics that can happen in the normal dispersion regime. So this is the regime where the solitons are not usually observed. Of course, if you also consider the anomalous dispersion regime, you will have very different behavior, very different dynamics and possibilities. Let us now see how the Kerr nonlinearity will affect the spectrogram of the pulse. What we can see, this is that in presence of nonlinearity that induce cell phase modulation, the energy is this time redistributed along the frequency axis, so along the vertical line of our spectrogram. And how will evolve the spectrogram will be dictated by the temporal gradient of the intensity profiles of the input pulse. So to finish this introduction, let us now consider what happens if we combine both dispersion and nonlinearity, and if we start with a pulse evolving in a purely nonlinear medium followed by a purely dispersive medium. So what we can clearly identify on the spectrogram, this is that in the first stage of propagation, the cell phase modulation enhances the spectrum and it increases its spectral extent. And in the second stage of propagation. We use this time anomalous dispersion, and it will bring together the different spectral components so that in the temporal domain the pulse will be compressed. So we have here a very powerful way to generate pulses that are shorter than the input pulses. And this is in fact well known from now 3 decades. It has been used many times. What is perhaps a bit less known, this is what happens when you swap the two segments. So if you start by purely dispersive medium and then use a second fiber with a very high nonlinearity. So in the first stage, the anomalous dispersion will stretch the pulse, so it induces a different delay. And in the second stage, the cell-phase modulation will lead not to a broadening of the spectrum, but it will lead to a narrowing of the spectrum. So this is a bit less usual, the fact that the cell-phase modulation can lead to shorter spectrum after propagation. So we will see example of such spectral compression in a few works that I will detail a bit later. So let us now discuss some more concrete example with various experimental results. So it is possible to generate, starting from a Gaussian pulses, a parabolic pulse. So what has been shown, this is that an initial Gaussian pulse, during its passive propagation into a normally dispersive fiber, can reshape into an intensity parabolic profile. But in order to see this nonlinear reshaping, you have to choose the right input power and the right propagation distance. And here, normal dispersion is absolutely mandatory. So we have tried to see if it experimentally works or not. And here is a typical setup that we have developed at the University of Burgundy. All our setup are based on standard telecommunication components. So we work in the C-band of optical communication around 1550 nanometers. So we start with a picosecond modlock laser running typically at 10 gigahertz. We can tune its temporal duration using an optical bandpass filter, and we amplify this pulse strain to the right peak power using an erbium dot fiber amplifier, and we launch the resulting signal into a spool of normally dispersive fiber. So this is, in this case, a spool of 6 kilometers of non-zero dispersion shifted fiber. And directly at the output of this fiber, we use an optical sampling oscilloscope, which enables us to have directly the output temporal intensity profile with a picosecond resolution. And here are the measurements that we can obtain. So here we have made measurement according to the input power launched in the fiber. So this is in some extent similar to changing the propagation length in the fiber. And what we can see, this is that the input Gaussian pulse is strongly reshaped, and at a given stage of the propagation for a given power, we observed a parabolic intensity profile. But we can see that if we increase the propagation length of the input power, then the parabolic profile is not maintained upon propagation. So what we have here, this is only a transient stage of the propagation of the pulse. So the good point this is that we have a parabolic pulse. The bad point this is that this is just a transient stage. There is in fact another way to generate parabolic pulses in a normally dispersive fiber, which is a bit more elegant. And to have the second way of generation of parabolic pulse, what you need, this is the addition of some gain, of some distributed gain along your fiber. And in this case, let's see how the spectrogram will evolve. What we will observe, this is a strong reshaping of the intensity profile towards an inverted parabola, and once this inverted parabola is obtained, the shape is maintained. It just undergoes some temporal stretching. Well, it also undergoes, along the propagation, some spectral reshaping, and we can see that the input Gaussian spectrum is also reshaped into a parabolic spectrum, and then it continuously increases its spectral wave. And now, if we consider the chirp, what we can make out, this is that we have a highly linear chirp, which is a good point for applications. So here, what we have, this is a very nice example of self-similarity. We have a parabolic shape that is maintained, experiencing some temporal and spectral broadening at the same rate, as well as an increase of its peak power. So this typical waveform has been called a similar return. And in experiment, we have checked that this is possible to generate them. So what we can add to the previous experimental setup, this is just a Raman punt in order to provide a distributed gain in the normally dispersive fiber. And if we compare the result obtained in the passive configuration with the result obtained in presence gain, what we can now see, this is that the parabolic intensity profile is now maintained upon propagation. So we have here the shape that does not flatten over further propagation. So we have here on this example the demonstration of a similar return. So we are not the first to demonstrate this waveform, and if we have demonstrated them in Raman amplifier, they have been previously demonstrated in 2000 in ether-doped fiber amplifier, and then later in air-doped fiber amplifier. It is also possible to mimic a physical amplifier by using a progressive decrease of the dispersion. So using a dispersion decreasing fiber, you can also generate parabolic pulses. And in fact, if you have a fiber cavity with a gain segment, fiber gain segment, you can also observe the generation of parabolic states in your cavity. So those parabolic pulses, they have excited a lot of various applications. First, in the domain of ultra-short pulse generation, because as we have seen on the spectrogram, their chirp is strictly linear. This is a real advantage for them compensate this chirp and to lead to high quality femtosecond pulse. They have also stimulated some investigation in the context of optical regeneration of optical communication. And one last application that they have motivated, this is perhaps not the most important application, but this is the one that I will present in this talk. This is the application to the field of spectral compression. So here is a small video of what we have been able to do in the lab. So here is the spectrum of our laser source that has been parabolically shaped, and what we observe here, this is the change of this output spectrum when we increase the power in a highly nonlinear fiber. And what we can see, this is that the spectrum gets narrower and narrower, and we can with this technique of spectral compression, decrease the spectral width of our parabolic pulse by a factor of more than 10. And now, if we compare the result that we can achieve using a second parabolic pulse with the result with a similar pulse but with a parabolic intensity profile, we can see that the parabolic shape leads to significant improvement both in terms of side lobes but also in terms of spectral brightness that can be observed at the point of spectral focusing. And what is also quite interesting, this is the evolution of the phase at the central frequency in this transformation. So what we observe, this is that the phase of the pulse evolves during the process of nonlinear spectral compression, and at the point of spectral focusing we have a typical phase shift of half a pi. So the video was a simulation, but we have also been able to confirm those predictions running an experiment not at the wavelength of telecommunication. It was around 1 micron, and the experiment was carried out in Marseille. And here what we have, this is an analogy with the well-known phase shift, the well-known Gouy phase shift. And usually this Gouy phase shift is associated with a linear process such as diffraction or dispersion. Here this Gouy phase shift is induced by nonlinearity in an optical fiber. So this analogy was quite nice. So let me now say a few words about the generation of a second waveform, which is this time triangular. And you can generate this triangular pulse using a Gaussian pulse. But the difference compared to the passive propagation of a Gaussian pulse leading to a parabolic profile, this is that this time we start with a Gaussian pulse with some initial linear chart. So using this linear chart, it adds some extra flexibility on the nonlinear reshaping, and in Aston, Sonia Boscolo have shown that for a well-chosen input power and a well-chosen propagation of the pulse, we can observe at a given propagation length the typical triangular intensity profile. So what we have again tried to do, this is to check if experimentally it works or not. And what we have done, this is again use our gigahertz picosecond modlock laser. We have used a purely dispersive fiber in order to induce the input linear chirp. We amplified the chirp pulses by an EDFA, and the nonlinear reshaping takes place in a normally dispersive fiber in presence of nonlinearity. And we can see that the input pulses have strongly reshaped, and we observe the typical triangular shape. So having this shape, we have had an extra spool of fiber, but this time it was a fiber of a highly nonlinearity. So we can neglect here the dispersion. This is why the intensity profile does not change so much. It remains very close from a triangular waveform. But here the interest was in fact in the evolution of the spectrum and the spectrogram. The triangular intensity profile, one of its main characteristics, this is that you have a constant gradient in your intensity profile. And this constant gradient will induce, by surface modulation, a shift of the energy that is contained in the leading and trailing edge. And as the gradients are of opposite side, the energy will be shifted towards opposite direction. So, as we see in the animation of the spectrogram, the energy in the leading edge will be shifted towards lower frequency, whereas in the trailing edge, the energy will be shifted toward higher frequencies. So at the end, the energy will be clearly concentrated into two spectral peaks, and they are very well separated. So let's see now if experimentally we can check it. So once again here we show this is the evolution of the output spectrum according to the input power. So we slowly increase the power launched in the highly nonlinear fiber, and we can check that the energy gets more and more concentrated into two peaks that are very well separated, and we can easily play with this spectral separation by changing the input power. So after now discuss these two rather simple waveform, I will here say a few words about one of our latest works that deal with flaticon pulses. So what we consider now as an input wave to a normally dispersive fiber, this is not a pulse signal anymore, this is a continuous wave, but with its phase that is modulated. So we use here in this example a phase with a triangular modulation. So if you have well understood the previous example, as a triangular modulation of the phase will lead to the concentration of the energy in two different peaks, two different frequencies. And we will be interested in the evolution of this continuous signal during propagation in a fiber where the nonlinearity dominates the effect of dispersion. And what we can see this is that we observe a kind of piston effect where the continuous wave does not remain continuous at all. It becomes a pulse signal with a flat part, with oscillation in the wings, and with the energy that gets concentrated in the neighborhood of the central frequency. So we have here different nonlinear dynamics that acts simultaneously. We have first as nonlinear compression. We have here, can recognize a very flat part which is chop free, and this central part is surrounded by edges where we can see here some oscillations that are typical of a shock. Now if we look more closely to the evolution of the intensity profile, in this new simulation we have used this time a sinusoidal input phase modulation. It does not change qualitatively the conclusion. What we can observe in this simulation, this is once again that the central part of the pulse is very flat, so this is why we have called them flaticon. We can here clearly see the oscillation in the edge of the pulse, and if we look at the longitudinal evolution, we can see that we have in this example also a self-similar evolution. Once this shape is generated, it is maintained upon further propagation. It is maintained for the central part as well as the oscillation that are present in the wings. And all the interest in this new kind of waveform was driven also by an analogy that can be made with another field of physics, with the field of hydrodynamics, because we can draw a parallel between the evolution in a normally dispersive fiber with high nonlinearity and the evolution of an hydrodynamic wave in shallow waters. So here our flaticons, they can be potentially a way to explain the degeneration in sneaker wave. They are shallow water work wave. Here this kind of wave is a bit different from the wave that can be generated in the ocean, and they will be detailed later in another talk, I think by John Delay. So, a few words about the experimental confirmation. Here, the hardest point in this experimental demonstration was in fact to induce the phase modulation required to observe the reshaping. Here we needed a few pi's of amplitude for the sinusoidal phase modulation, so we have to develop a non-made technique. And when we compare the result of the experiment with the numerical simulation, we can see that we have a pretty good agreement. Here we do not use any fitting parameters, and we can also check experimentally that we have a self-similar behavior. Once again, the experiments are in clean agreement with the numerics. So this is now time for me to conclude this talk. So what I have tried to show in this presentation, this is that the concept of nonlinear shaping is powerful, but this is also quite simple to implement. It may offer many possibilities to tailor both the temporal and spectral content of a pulse. And even if the equation that rules the propagation seems very simple, it already includes a very large variety of the various dynamics, so that we can imagine a lot of different applications. What is really important in those different experiments, this is to find the good ratio between the impact of nonlinearity and the impact of dispersion, and to find the optimum length of fiber. So here what I have not gone into the details, this is all the work that we have done around the design rails to find really the optimum parameters. What I have also tried to show in this presentation, this is that when you start to play with the phase profile of the input pulses, if you try to change the input chirp, then you have another degree of freedom, and this is possible then to see new effect. And I think that the initial phase modulation is often neglected as a potential degree of freedom. Here I have mainly concentrated on nonlinear shaping alone, but this is possible to combine a linear shaping, usually done in the spectral domain, with all the potentiality that are brought to by the nonlinear shaping. So we can here imagine an hybrid device to take advantage of both worlds. And finally, the different things that I have shown, such as spectral compression, generation of similar pulses, they can be also included in a fiber cavity. So here there are in fact some basic building blocks, and this is possible to imagine some lasers delivering triangular pulses. Theoretically, Sonia Boscola has already shown it.